Okay, so the first thing is exam 3 is a week from today. So that would be the 24th. And the topics for that, there's not going to be any conservation laws on it. It's just up through circular motion. So on Monday, if you're studying over the weekend or something and you have some questions on problems related to the exam or any kind of questions related to the exam, bring them on Monday and I'd be happy to answer those, okay? Any questions about the logistics of the test? Yeah.
I had a question about our final. When is that?
Man, I still haven't seen that. I got it used to always be on the website, but I must not be looking in the right place now, so I got to find out.
Because my other classes, I have the dates for those. I just wanted.
Okay, yes. Okay, I will find out. I'll try. If you remind me after class, I'll do it after class.
Okay, got it.
Okay, thank you. Any other questions? All right, so, well, any homework questions you'd like me to go over? I assigned some conservation and momentum questions. I think most of the time those are not too difficult. It's really just a technique that you need to kind of remember you have available to you. When do you use conservation of linear momentum? This is the most important thing to know about conservation of linear momentum.
Collisions.
Collisions. That's when you do use it. When don't you use it? When there's no collisions, exactly. And that's the beginning and end of the story, okay? So now we're talking about conservation of mechanical energy. And I'm going to, just like last time I started with the punchline, I'm going to start with the punchline now, because once you get, there's so much setup for understanding little subtleties about it, but once you get through to the equation and doing problems, it's very easy to use. So conservation of mechanical energy says this. If all work on an object is done by conservative forces, then the kinetic energy plus the potential energy at instant 1 is equal to the kinetic plus potential energy at instant 2. Okay, this is also assuming that there's no heat and electricity and that kind of stuff that are important. Let's see. Oh my Christ almighty. Okay. A conservative force is a force where if you're given the object's location, you know the force that it applies to the object, okay? And there are two types of conservative forces that we're going to use. So really, practically speaking in this class, all you need to know is the only forces that do work need to be either gravity, gravity and or forces applied by springs. Those are the only two forces that we have potential energy functions for, and so you can't do it with anything else. Okay. Okay, the next question is, so I didn't say that the only forces acting on the object are conservative forces. So, hold on. Did that go through? All right. I didn't say the only forces acting on the object are conservative forces. I said the only forces that do work. So the next question is, are there any non-conservative forces that don't do any work? And the answer is there's two important ones. Okay, so there are two important non-conservative forces that do zero work. The first one is a normal force in rolling and sliding. And the second one is any centripetal force during circular motion. Most of the time for us, let me write that. What does centripetal mean? Yeah, very good. So any centripetal force in circular motion. What's the centripetal force we see most often in circular motion? Well, that's an acceleration, not a force. The most common force that we see is something attached to a string swinging around. Then that force is pointing toward the center of the circle. Okay? So this would be like cable tension. Okay? So the simplest practical description is that we can use conservation of mechanical energy in this class if the forces on the object are a combination of gravity, bless you, spring forces, normal forces in rolling and sliding, and centripetal forces in circular motion. Okay? So let's go through some problems. I guess I'll put these here just for reference. Gravitational potential energy is the object's mass times 9.81 times the object's height. the spring potential energy is 1/2 times the spring stiffness times x squared, where x is how far the spring is moved from its resting position. And kinetic energy is always calculated the same. That's 1/2 times the mass times the speed squared. Okay, so I think probably if all you read was starting here at simplest practical description, this is all you need to know how to use these problems. The other stuff that I said on Monday, it just helps you kind of understand a little bit where this stuff is coming from. By the way, why do normal forces and centripetal forces in circular motion do no work? If you remember what work means, positive work means in some sense that the force is in the same direction as the object is moving. And negative work means the force is within 90 degrees of being opposite the direction the object is moving. Remember that? Okay, well, normal forces in rolling and sliding and centripetal forces in circular motion are two cases where at every instant the velocity is perpendicular to the force. Well, if the velocity is perpendicular to the force, then the object isn't being sped up or slowed down. Energy isn't being increased or decreased by the force. Okay, so actually let me put this here. These are cases where the object is moving perpendicular to the force. And so therefore they don't do any work. All right, let's just go through some examples. Let's say that you have a skier at the top of a hill. Okay. And let's say that the hill has a height of 10 meters. That's not much of a ski hill, but if the skier is, and let's give the skier a mass, although it turns out that that wouldn't matter. So let's say there's a 50 kilogram skier is at rest at the top of the hill. How fast is the skier moving at the bottom if there's no friction? Okay, well, the first thing we have to do is make sure that we can use conservation of mechanical energy here. The first sign that maybe conservation of mechanical energy is a good approach is that we're talking about a relationship between a location and a speed. Do you see that? We're saying the location is the bottom of the hill. How fast is the skier going? So that's always a hint that maybe this is the way to go. So now we're going to think about the forces. So if we draw a free body diagram of the skier, at some point during the motion, there's a weight force. There's a normal force. It says there's no friction. mg is a conservative force, so that's fine. We have a potential energy function for that. The normal force is non-conservative, but that's still fine because it does no work. It's one of those forces that does zero work. Okay? So everything looks good for using conservation of mechanical energy here. And now I'm going to make just a little table. And I'm going to think about two different instants. Instant 1 is when the skier is at the top of the hill, and instant 2 is at the bottom of the hill. Okay? And conservation of mechanical energy says at both of these two instants, we want to calculate the total potential energy and the total kinetic energy. Okay, well, let's start with the potential energy due to gravity at the top of the hill. Okay, we're going to calculate this as the mass times 9.81 times the height. There's one more question that we have to figure out. What are we going to call zero height? There are a lot of like reasonable places that you might think of as zero height. The ground might be one of them. The center of the earth might be one of them. The center of the solar system might be one of them. You know, and so what do you think the deal is with the height? Well, the key thing is, you understand what so like we're going to put the height into this formula here, mgh. What are we measuring the height compared to? Well, if you look at this equation, notice that all that's going to matter is the difference in potential energy, which means as long as you're consistent, you can choose anything you want as your height equals 0. Okay? I usually just choose the lowest point in the problem I'm doing. Okay, so I'm going to call this height equals 0 at the bottom of the hill. But you could do it at the top of the hill too, or somewhere in the middle, or wherever you want. So the gravitational potential energy then at the top of the hill is the mass, 50 kilograms, times 9.81. And what's the height at instant 1? 10. And so this all comes out to be 4905. And I said that the SI units for all forms of energy are joules, so I'll put this as joules. And now let's calculate the kinetic energy at the top of the hill. The kinetic energy is 1/2 times the mass times the speed squared. What's the skier's speed at the top of the hill? 0, yep. And so there's no kinetic energy at the top. Now we'll go to the bottom of the hill. The potential energy is 50 times 9.81 times 0. So 0 potential energy at the bottom of the hill. And now the kinetic energy at the bottom of the hill is 1/2 times 50 times the speed squared. We don't know the speed, so I'm just going to leave this as v squared. And now we'll add up everything in the left column and set it equal to everything added up in the right column. So 4905 plus 0 is equal to 0 plus 1/2 of 50 is 25. So 25 v squared. So 4905 divided by 25 says v squared is equal to 196.2. Take the square root of both sides, and you get that v is equal to plus or minus 14.01 meters per second. This is a speed, not a velocity, so negative speeds don't make any sense, so we'll take the positive. I want you to notice something amazing about this. Like, notice how I drew the hill here. The fact that these are conservative forces mean that this is the answer no matter what the shape of that hill is, okay? It could be going up and down like a sinusoidal curve the whole way. It could be straight down. It could be fast down and then run along the flat for a while. This is all assuming there's no friction, which is a good assumption in some cases and not so good in others, but that's the answer. So you can see that's a pretty, in the right setting, it makes calculations that you wouldn't be able to do using Newton's laws really quick and easy. Okay. Anybody have any questions yet about that? Okay, let's do another one. So this time, let's say it's a skateboard. And this skateboarder I don't know why he's so sad. Skateboarding's fun. So say this skateboarder is moving along the flat and is heading towards a hill. And we want to know how fast the skateboarder needs to be moving to get to the top of this 2-meter tall hill. So how fast does the skateboarder need to be going at the bottom to reach the top of the hill? This time I won't give the skateboarder's mass, and we'll see that that cancels out of the equations, which means this answer is the same no matter what mass the person had. Okay. Okay, well, let's think a little bit about what this means. So if we're trying to find out what speed is required at the bottom to get to the top, the slowest the skateboarder could be moving at the bottom to make it to the top is if he just gets to the top as his speed becomes 0. Okay? Does that make sense? We're going to assume that what we're saying is we're looking for a relationship between a location at the bottom of the hill and a speed compared to a speed of 0 at the top of this hill. So again, we have a relationship between location and speed. Do you see that? And so again, that should make you think like, okay, talking about speed, especially if it's talking about speed instead of velocity, because with velocity vectors, we do a lot of kinematics and stuff with components. There really isn't anything else where we only care about speed and not direction. So that's a hint that you want to use conservation of mechanical energy. Now let's see if we can use it. Okay, so Okay, there's the free body. The force is our weight. And then a pushing force from the ground. Those are both in our list of accepted things. This is conservative. This one is non-conservative but does no work. So now we're feeling pretty confident that we can do this problem using conservation of mechanical energy. So now I'm going to set up a table again. Instant 1 is at the bottom of the hill. And instant 2 is at the top of the hill. What do you want to choose as our height equals 0 in this problem? Someone pick something, I'll use whatever you say. Center of the Milky Way galaxy, then we'd have to put in billions of miles or whatever. Who said something? Bottom of the hill? You could use the top and then you just have negative heights for everything, which would seem a little weird, but it would work fine. So the gravitational potential energy is the mass. All we know for that is we're going to call it m, times 9.81, and times a height of 0. So there's 0 gravitational potential energy. Then the kinetic energy at the bottom of the hill. We don't know how fast the person's going in this case, so we're going to call that v, and that's what we're going to try to solve for. So this is 1/2 times the mass m times v squared. At the top of the hill, the gravitational potential energy is the mass times 9.81 times what's the height at the top of the hill? 2, yep. And then for the kinetic energy, we have 1/2 times the mass times, at the top, we're assuming the skateboarder has just reached the highest point and stops right at the top, so the speed is 0. And so conservation of mechanical energy says 0 plus 1/2 mv squared is equal to 19.62 m plus 0. So 1/2 mv squared is equal to 19.62 m. Now you can divide m from both sides, and those cancel out, meaning that the answer we're going to get doesn't depend at all on the person's mass. It would be the same for a, 250-pound person as a 50-pound person. Multiply both sides by 2. We get v squared is equal to 39.24. Take the square root of both sides. And in order to get to the top of that 2-meter hill, the person needs to have a speed of 6.26 meters per second. And positive. And the thing where instead of putting in a mass, we just used an unknown m and then it canceled out. The same thing would have happened in the skiing example, because notice every number we have here is multiplied by 50. So no matter what that is, it would cancel out. Okay, let's do one with a spring. So let's say you have this cart that's attached to a spring. The cart has a mass of 2 kilograms. And it's attached to a spring that has a constant, a stiffness constant of 400 newtons per meter. So let's say we pull the cart back until the spring is stretched 8 centimeters from its resting length. So we'll pull it back 8 centimeters from rest. And we want to know what's the speed of the cart as the spring moves past its resting length. Okay, so let's talk for a second about what's going to happen when you release this thing, if we're assuming no friction, no energy losses. So if you stretch this spring by pulling this back and let it go, it's going to oscillate back and forth, okay? It's going to go from 8 centimeters stretched, go this way until it's 8 centimeters compressed beyond its resting length, and then it's going to go back. This wouldn't work if that spring, you know, a lot of times you see springs that are, like when they're at their resting length, all the coils are touching each other. That wouldn't work. You'd have to stretch it out so that it can compress and stretch. But it would go from 8 centimeters on this side to 8 centimeters on this side, then go back and forth and back and forth. And every time it goes back and forth, it passes the spring's original resting length, the place where this would just sit still. Okay, and that's where we want to calculate the speed. Okay. Well, again, this is a relationship between speed and location, so that suggests maybe conservation of mechanical energy is the way to go. Well, in fact, in this class, springs, we've only done this calculation with energy, so anytime there's a spring, it has to be energy. There's really no other way you can calculate anything, okay? So now let's think about the free body diagram and make sure that all the forces are allowable. There's a spring force. That's okay, because that's conservative, and we have a potential energy function for that. And then there's a normal force. That's okay. It's non-conservative, but it does zero work. And so now we're feeling confident about this. And so I'll set up instant 1 and instant 2. And I'll think of x is equal to 8 centimeters here. And remember, the definition of x for these spring calculations is how far the thing is from its resting length, how far the spring is from its resting length. So when you stretch it 8 centimeters, x is 0.08. When it passes its resting length, what's x equal to? 0, because it's at its resting length. So x is equal to 0. Okay, now, oh, and I skipped something important actually. I forgot to put the weight in there. There is weight, right? The weight is 2 times 9.81. All right, so this time we're going to do potential energy for the spring and potential energy for gravity and the kinetic energy, okay? For the gravitational potential energy, where do you want to have our height equal to 0? Might as well have it, I mean, the thing is the same height the whole time, right? So we might as well just say the height is 0 for the whole thing. You'd get the same answer if you chose a different location, but this will just take some of the numbers out of the calculation. So our gravitational potential energy is 2 times 9.81 times a height of 0 and 0. Next, we'll do the spring potential energy. That's 1/2 times 400 times 0.08 squared and you get a spring potential energy of 1.28 joules. And now the kinetic energy. Well, we're going to assume that it's pulled back and released from rest. The person isn't, pushing it as it leaves. And so this is 1/2 times the mass times 0 squared, or 0. And now we'll go to when the spring is at its resting length. The gravitational potential energy is 2 times 9.81 times still a height of 0, so this is 0. The spring potential energy is 1/2 times 400 times 0 squared, because x is 0. And so this also comes out to be 0. And then the kinetic energy is equal to 1/2 times the mass times the speed squared that we're trying to calculate. That just comes out to be v squared. Conservation of mechanical energy says 0 plus 1.28 plus 0 is equal to 0 plus 0 plus v squared. So v squared is equal to 1.28. And so the speed when the length is 0 is 1.13 meters per second. This is sort of an aside. Haven't given you any problems or I won't give you any daily problems like this. I don't know, maybe I'll put something like this in a weekly assignment. But how would you calculate that spring constant, that 400 newtons per meter? So say that that's not given to you, and you want to do a calculation involving springs, and you just have a spring sitting in your drawer, you know? It doesn't have any numbers on it. So how do you calculate that? Hang a mass some mass M from something, and measure how far the spring stretches. So you can say, like, here was the thing before you let it go, and this is the deformation. We'll call it X. Then that spring constant is equal to mg divided by x. So if the mass is 0.1 kilograms, and it makes the spring stretch from its resting length 2 centimeters, then the spring constant is 0.1 times 9.81 divided by 0.02 and in this case you'd have a spring constant of 49.05 newtons per meter. Okay, I'll sort of separate this from the rest of the stuff, but okay, conservation of mechanical energy and conservation of linear momentum often can be combined into problems that where multiple things happen, mousetrap game type stuff, one event following another. If you see something with a collision in it, but then other stuff happens, consider that it's very likely that you're going to use conservation of linear momentum for the collision part, and then conservation of mechanical energy for the rest of the stuff. Okay, so let me do an example like that. So this is combining conservation of linear momentum with conservation of mechanical energy. So let's say that we have a spring. This is like the spring of a, like starting a pinball game. You pull back the plunger, and so we have this spring like that, and we have a little cart. And let's say this cart is 0.2 kilograms. And then over here, we have another cart of 0.1 kilograms. And we're going to pull this spring back, let it go. It's going to launch the bigger cart. It's going to collide with the second one, and they're going to latch together. Okay? So we're going to release the spring. The carts will latch together. And we want to know what's the velocity. Let's do this as a vector. What's the velocity vector of the carts? After the collision. Okay. We have to know how stiff this spring is. Let's say that K is equal to 600 newtons per meter. And let's say it's pulled back 2 centimeters. So 0.02 meters. Can everyone picture what's going on in this? Okay, well, the part that we're going to use conservation of linear momentum for is just the collision part, just right before the collision to right after the collision, okay? So anything else happening in the problem, be ready to use conservation of mechanical energy for that. That's almost always what you're going to have to use, okay? So the first thing we're going to do is figure out when we release this spring, how fast the 2 kilogram cart is moving, okay? So part 1 is to find the speed of the cart after it's released. Well, let's make sure that conservation of mechanical energy can be used here. We have a weight force of 0.2 times 9.81, so that's 1.962 newtons. We have a normal force N. We have a spring force Fs. And so, yeah, we got gravity, we have the spring force, we have the normal force, so we can use conservation of mechanical energy. I'm going to choose my height equals 0 to be just, the height never changes. So let's set it up so that the potential energy due to gravity is just 0 the whole time. Okay, so at instant 1, the gravitational potential energy is 0 because of our choice of height equals 0. Potential energy due to the spring is 1/2 times 600 times 0.02 squared. So that is 0.12 joules. The kinetic energy, we're releasing this cart and this spring from rest. So V is equal to 0, so kinetic energy is 0. Because the speed is 0. Then at instant 2, we've released the spring. The gravitational potential energy is still 0. The spring potential energy, it's not even touching the spring anymore, so we don't have to worry about that anymore. The spring potential energy is 0. And the kinetic energy is 1/2 times 0.2 times V squared. And so that is 0.1 V squared. So now set up the equation. We have 0 plus 0.12 plus 0 is equal to 0 plus 0 plus 0.1 V squared. So 0.1 V squared is equal to 0.12. So V squared is equal to 1.2. So V is equal to 1.0, I guess let's round that to 1.10 meter per second. So now we know how fast that thing is moving before the collision. Now we can do part 2, which is conservation of linear momentum for the collision part. Okay, so we have this cart moving this way at 1.10 meters per second, and it has a mass of 0.2 kilograms. And the other cart is just sitting there at rest, and it has a mass of 0.1 kilogram. To use conservation of linear momentum, the net force on that system outside of colliding with each other has to be 0. Well, this is moving in a straight line. There's no accelerations, so there can't be any net forces. I mean, it's moving in a straight line with a constant speed, so there can't be any outside forces. And so we can set this up as conservation of linear momentum says 0.2 plus times the velocity vector of 1.10 plus 0.1 times the velocity of 0 is equal to the sum of the masses times a velocity vector. The x equation says Vx is equal to 0.73 repeating. The y equation says Vy is equal to 0. And so together, these say that after the collision, the velocity is 0.73 repeating, 0 for y, or in other words, moving in this direction at 0.73 repeating meters per second. So just from knowing some properties of this spring and how far you pull this spring back before you let it go, you can figure out what the speed of this system is once those two things latch together. Any questions about that? Okay, let me do one more example. How much time do we have? Yeah, I can do this. This is called a ballistic pendulum. And have you ever thought, like, I don't know, like, what year do you think videos could be taken fast enough to measure the speed of a bullet coming out of a gun? I don't know the answer to that, but I mean, I bet it's pretty recently, right? I mean, there have been guns for a long time before that was a possibility. So how do you think people measured the speed of bullets coming out of a gun before high-speed video? That's pretty important information to have for calculations and just for parameters to put on guns that you're selling, whatever. But they did used to be able to measure that speed, and they did it with this thing called the ballistic pendulum. So what you have is a mass that's hanging from some kind of string. They actually set it up with multiple strings so it's more stable. Let's say this is 1 kilogram. And this is like a block of wood or something that a bullet is going to enter but not come out the other side. Okay. And you shoot a bullet into this thing. Let's say that the bullet has a mass of 0.005 kilograms. And let's say it's moving at, well, we don't know what it's moving. That's what we're trying to find. Okay. And let's say that after the bullet becomes lodged in the block, this thing swings up to a position like that. And what we see, and notice this is all easy stuff to do just by eyeballing it, you know. You can just be watching the wall and see how high this block swings up. Let's say that it swings up a height of 0.4 meters. What was the speed of the bullet? Well, again, we're going to use conservation of linear momentum for the collision part. And we're going to use conservation of mechanical energy for the mass swinging up, okay? And combining those two things, we'll be able to calculate that V. So I'm going to sort of work in reverse. So I'm going to work in reverse order. So part one is to calculate the speed of this mass at the bottom of its bottom position that would allow it to swing up 0.4 meters. So the speed of the mass at the bottom required to swing up a height of 0.4 meters. Okay, so its height is going to change by 0.4 meters. Let's think for a second about, just think about a free body diagram for a second. What forces are acting on this? There's a weight, that's the mass times 9.81. The mass is pretty much 1 kilogram, but I'll put in the mass of the bullet too because it's in there, okay? So it's 1.005 times 9.81. So that's 9.86 newtons. And then the only other force is the cable force. But notice the nice thing about that cable force is this mass is in circular motion, and that cable force is pointing toward the center of the circle. Okay? So it does zero work. This is a centripetal force. And so the work is equal to 0. And so we can use conservation of mechanical energy. We have an instant 1 and an instant 2. Bless you. For height equals 0, I'm going to choose this. So the height at the bottom of the swing is 0, and the height at the top of the swing is 0.4. The gravitational potential energy is the mass, 1.005 times 9.81 times 0. The kinetic energy at the bottom is 1/2 times 1.005 times the speed squared that we're trying to calculate. At the top of the swing, the gravitational potential energy is 1.005 times 9.81 times 0.4. So that's 3.94 joules. And the kinetic energy at the top of the swing, well, when it reaches its highest point, it's just about to turn back around the other way, so what's its speed? 0, yep. And so we have 0 plus 0.50, I'll just call it 0.50, is equal to 3.94. Sorry, I left off the v squared here. So 0.50 v squared is equal to 3.94 plus 0. And so v squared is equal to 7.89. And so the speed at the bottom of the swing is 2.81 meters per second. Okay, well now we have to use conservation of linear momentum. This is part 2. Now we have to back calculate, sort of calculate in reverse, the speed of the bullet given that after the collision, the system speed is 2.81. Okay, so we're going to say, we know that before the collision, the bullet is moving in the positive x direction. We know right after the collision, if you think of a tangent to that circular path, the block is moving in the positive x direction, right? If there's your circular path down here, the velocity is this way. So everything's moving in the x direction. So we'll say the bullet's mass times its unknown velocity, which is this, plus the mass of the block times its velocity vector before the collision, is just 0, is equal to the combined mass times a velocity vector of 2.18 for x, 0 for y. So the x equation says 0.005 plus 0 is equal to 2.82. I left off the v here. And so v is equal to a very slow speed, well, whatever, 564.81 meters per second, a little over 1,000 miles an hour. Maybe that's not so slow. I don't know. I don't really know anything about gun speeds. Yep.
So for the velocity, never mind, sorry.
Okay. The y equation tells us that, there's no y component. So anyways, you get a velocity of 564.810. And so now without a high-speed video camera, we've used just what we can do with our eyes and some calculations to figure out the speed the bullet was moving when it collided with that block. Any questions about that? Okay, that's all.